Good evening. This is Professor David J. De Los Reyes, a graduate of Electrical Engineering. Okay, my topic tonight will be a very interesting topic. Okay, let's proceed. I am now on lesson number 81 on my channel, still on the topic Integral Calculus, subtopic length of arcs. And the main topic as an application of the length of arcs will be the length of transmission lines at different level, meaning the computation of the total length of the transmission line if the towers are at different levels. Okay, I will try to read the problem. This is a transmission line problems for electrical engineers. Okay, let's proceed. Find the length of a transmission line if the distance between the towers is 400 feet. The distance between the towers is 400 feet. The height of the towers is 40 feet. The height of the towers is 40 feet. This is 40 feet. Okay? The other tower is 40 feet higher from the ground level, meaning the first tower is at a lower level than the second tower. The second tower is 40 feet higher with respect to the first tower. So this is 40 feet. Their difference in height with respect to their base is 40 feet. And the height of the towers is 40 feet. You see it, guys? This is the flat ground level. The distance between the towers, if we try to measure it on the, what they call this ground level, it is 400 feet. You could do that by surveying, by using your transit. This is civil engineering already. You could measure the distance from the first tower and second tower by using a transit, and that for the civil engineering, what they call this subject. Okay? This is the transmission line. Okay? This is 400 feet. This is 40 feet. 40 feet. Okay? The question is asking for the total length of the transmission line. The total length, the one in red. Okay? It looks nice, right? This is an uphill thing, meaning the second tower is uphill and the first tower is actually on the ground level. Okay, the distance horizontally, if you try to use the measure it by using a transit for civil engineers, it's 400 feet. Okay, let's proceed. This will now be an interesting application of integral calculus. Okay, let's proceed. If we try to assume that the curve is actually a parabola, hold on. It seems this is one half of the parabola, because if we try to expand the figure of the, what do you call this, figure of the, okay, see, you see it? So this is actually the parabolic curve, and it seems for the meantime we are just given one half. So if you try to project the other half, okay, then try to visualize, it looks like a parabola. A parabola opening apart. Okay? So if this is half of the parabola, this should be the location of the vertex. Okay? And this point here is at the other end of the transmission line. We don't have any transmission line here. I just project it for us to visualize that the corresponding curve of the parabola will be something like a parabola, or curve of the transmission line acts like a parabola. Okay, let's proceed. The equation of a parabola that opens upward is actually, in general, this is x minus h quantity square equal to 4p times the quantity y minus k. this h and k refers to the location of the vertex. Okay, and from our figure, the vertex is actually, the abscissa at the vertex is 0, and the height is actually the height of the transmission line. So actually, our h is 0, the abscissa of the vertex. And the k, the ordinate, is actually 40 feet. Because 40 feet is the height of the tower with respect to the ground. Okay? So by using this equation here, we try to substitute h0, k0. This will become x minus 0 quantity square equal to 4p times the quantity y minus 4t. So x square now will be equal to 4p times the quantity y minus 4t. What is the significance of this equation here? Meaning the equation of this transmission line is actually this one. That's the equation of the transmission line. With the given specs, the distance is, between them is 400 feet. The height of the tower is 40 feet. And the direct differential level with respect to the ground level of the base of the transmission towers is actually 40 feet. So actually we got a problem here. Why? We do not know the value of P. For P is actually this distance here. If we try to explain it, this is 2P and this is 2P. So for a parabola, the one being mentioned as 4P is actually the distance from this point here to this. And for the meantime, we do not know the value. But we are given another point on the parabola, this point here. At this location here, the abscissa is 400, and the ordinate is actually 40 plus 40, that is 80. So actually, this 480 will should satisfy the variables over here. So we will take this value x equal to 400, y equal to 80. We place back on equation number 1. So what will come out? 400 square equal to 4p times the quantity 80 minus 40. Solving for 4p. 4p will be 400 square is 400 times 400, right? And solving for p, we will remove this one, we pull it under it. 80 minus 40 is actually 40. So actually, this 40 here cancel with this, so this will become 10. So 4,000 or 400 times 10 is actually 4,000. So the unknown value of P for the transmission line is actually 4,000. Okay? This came from the characteristic or the requirements of the problem. We use the requirements of the problem. The distance between them is 400 and this height here is 80 feet. So if we now try to compute for the equation of the parabolic curve of the transmission line, x squared now will be equal to 4,000. We're following this. Times the quantity y minus 40. And solving for y will be x squared over 4,000 plus 40. So actually, we are now given y as a function of x. Right? So if we are now given y as a function of x, there is no more problem. Why? Because under the so-called differential equation for length of arc, differential length of arc is equal to the square root of 1 plus dy over dx quantity squared times dx. We could compute for this one, right? So dy dx will be the first derivative of this one. This should be power formula 2x over 4,000 plus 0, or dy dx will be x over 2,000. Okay? Squaring both sides. Dy dx quantity square equal to the square of x is x square. The square of 2,000 is actually 4 million. 4 million. 2,000 times 2,000. 2 times 2 is 4. 1, 2, 3, 1, 2, 3. This is times 10 to the 6. 10 to the 6 is actually 1 million. So this is 1 million. Okay? So what will come out? Dy over dx quantity square equal to x square over 4 times 10 to the 6 or 4 million. So going back to this equation here, differential length of arc now will be the square root of 1 plus dy dx quantity square. This is x square over 4 million times dx. Okay? If we try to simplify this, 4 times 1 million, it will be this, plus x squared all over 4 million. 4 million is a perfect square, that is 2,000, right? So we could bring it out. So this is 1 over 2,000 rather, times the square root of x squared plus 4 million times the x. And this is now a differential equation. And to compute for the total length of the transmission line, we will integrate both sides. Okay? But it is not an easy integration. This falls under the powers of trigonometric functions, so we will use trigonometric substitution, okay? We will let x squared equal to 4 million tangent square of theta. Taking the square root of both sides, x now will be, the square root of 4 million is 2,000 tangent of theta. Taking the differential, dx now will be 2,000. The differential of tangent is secant square of theta, differential theta. Okay? We try to simplify this one. We do it separately. So x squared plus 4 million the square root, we place the substitution. What will come out will be 2,000 secant of theta as a function of the variable thing theta. Okay? Then I will try to bring out also a triangle. From this, tangent of theta is actually x over 2,000. Tangent of theta is x over 2,000. So the hypotenuse will be the square of this plus the square of this. The square of x is x squared. The square of 2,000 is 4 million, the square root. Why did I bring up this one? Because later on we need the value secant tangent theta, secant theta. So differential length of arc now will be equal to, we'll go back here. This is 1 over 2,000. The equivalent of this is 2,000 secant of theta, and dx is actually 2,000 secant square of theta, differential theta. 2,000 cancels, so we got 2,000 left. So what comes out is 2,000 secant square, secant theta will be secant cube of theta, differential theta. This is integrable by using powers of trigonometric functions. It's a complicated thing, I didn't show you anymore. But if you try to solve for this one using powers of trigonometric function, the integral of secant cube of theta, differential theta, we've done this under the integration. This is 1/2 secant theta tangent theta plus 1/2 the natural logarithm of secant theta plus tangent of theta. The solution of this is a very long one. I didn't show you anymore, but I just placed the answer for this one. I did it myself. The integral of secant cube of theta differential theta is 1/2 secant theta tangent theta plus 1/2 natural logarithm secant theta plus tangent of theta. Okay? We bring out the original variable. The original variable is x. So we will replace secant of theta and tangent of theta coming from this one. Secant of theta is this one. Tangent of theta is x over 2,000. So if you use your rough draft, try to compute for the product of secant tangent, what will come out will be this one. For the second one, it is 1/2 the natural logarithm. Secant theta plus tangent of theta, if you try to use your rough draft, then try to calculate, it will just be simply this one. The natural logarithm of x plus this square root all over 2,000. This is quantity. This whole quantity here should have the natural logarithm sign. The limit now is from 0 to 400. To compute for the total distance of the transmission line, x should move from 0 to 400. The abscissa here is 0, the abscissa here is 400. So our limit is actually from 0 to 400. The simplification of this, you could use this one by using your calculator. Do it in a rough draft, little by little. Okay, I didn't show you anymore. If I will try to, I did it myself, it's on my rough draft. The value of the upper limit is 0.403. The value of the lower limit will be 0. 0.403 minus 0 is 0.403. So if we try to go back here, okay, is it 2,000? 1 over 2,000. 2,000, hold on. 2,000. This is 2,000, okay. This is 1/2, this 1/2, I bring it out, so it becomes 1,000 times the equivalent of this one. What comes out is 0.403 times 1,000, and the total length of the cable is 403 feet. Theoretically. Okay? So the total length of the cable here is 403 feet. Okay? The solution is a little bit complicated. I expedited it, but I've shown you the steps. Okay? On the substitution of this one, I told you use your rough draft, use your calculator, try to solve for the value of the upper limit, then subtract the lower limit. What will come out will be 0.403 minus 0. It is 0.403, but this is to be multiplied by 1,000. So 1,000 times 0.403 will be 403 feet. That is how we compute the length of transmission lines using integral calculus. That is, if the level of the towers are not actually at the same level. Okay? You see it, guys? We got a ground level here, another ground level. We got the transmission tower here. We got a tower here. The distance between these is 400 feet. Okay. The height of the tower is 40 feet. This is also 40 feet. Okay. And it says that the other tower is 40 feet higher than the other one, so this should also be 40 feet. And if you try to connect the transmission line will be here. Okay. And from our computation, the total length is 403 feet. You see it, guys? Different levels. This is the original ground level. So if this is higher than the first tower, it could be that this is uphill maybe. Okay? In real life, it is like that. Do not always assume that the towers are actually at the same level, because in real life, we go to the mountains and we erect transmission lines, the configuration will be something like this. That is the importance of integral calculus, guys. So if you are the project engineer, you know that the distance between them is 400, the height is 40 feet, the other one is 40 feet higher. Your boss will be asking what will be the total length cable needed to erect from first tower to the second tower. Approximately, theoretically, it is 403 feet. Okay, good evening, Los Angeles.